hello, Mr. Aaron, Mr. Ryan, alright?
Yeah.
We talk about the knapsack, yeah? 01 knapsack, yeah? What's the problem? Can you describe to me what's this problem?
01 knapsack is when you're finding the capacity.
Anybody? So what's the problem about?
The problem.
There are, you have a bag.
I have a bag, a knapsack, yeah? That's good. With the capacity, C, yeah? Maximum
and you
capacity.
have weight.
Item, a few items, yeah? A few little item. Yeah, each one
And you
we
need
have
to
the
fit it
weight.
in your bag.
Weight, and then we have a value,
And you
yeah?
fit it in your bag.
And what's the objective? What's the objective?
You have a maximum weight.
Yeah. Okay, so yeah, to sum up, we have a few items and we want to put it in a knapsack with the capacity C and we want to maximize the values. Yeah, values. Each one has the value, for example, like value 1, 5, 3. And the weights could be something like 1, 2, 3, okay? And then the capacity could be of the knapsack is 5. So what's the optimum solution if we want to put the items in the bag, right?
2, 5 and 3, 3.
So which two items you would like to pick?
The middle one and the last.
Yeah, okay. 2 plus 3, that's not equal than 5. That's all equal than 5. And then the values we attempt is 5 plus 3. Okay, so that's the objective. Huh? That's the problem. And if we can describe the problem using the mathematics. Remember? Yeah. So let me just repeat again. Okay. So we have the V, which stands for values. It's an array. VI. Yeah. VI is the values, and then we have WI is the weight, and we have C, which is the capacity, maximum capacity of the knapsack, and we have the PI, which stands for the if we want to pick it, yeah, decide to pick it. So it belongs to it only has two values, 0 and 1, right? 0 and 1. 0 means that we don't pick it. The item, item, we don't pick it, and 1 means that we pick it. So we want to maximize, let's say, maximize what? PI, okay, sum of a PI times VI, right? Look, we want to maximize the total value we put on the knapsack, but we also want to make sure that the sum of the PI times WI, the weight, is less or equal than C, right? Okay? And then look, PI is 0 and 1. Okay, so that's the mathematical problem. That's what we call it 0.01 knapsack. 01, what's 01? 01 comes from here. Look, it only has two values. P only has two values, 0 and 1. Okay? Yeah? And we talk about what? We talk about what kind of solution have we talked about? What have we talked about? Talk about the solutions.
Dynamic programming.
Dynamic programming.
Minimization, bottom
Okay.
up, top down.
So it has two dynamic
Yeah.
programming. Yeah. Top down and bottom up. Yeah, bottom up. BU. Yeah. Top down is recursion.
TD and
With
bar.
recursion with the
Bar.
minimization, which we put a cache, and the BU is that we store the
DP.
values in the DP array. Okay, DP array. Okay, we're done. Okay, so let's review. Let's just quickly implement it. Okay,
And then the
shout out if you remember. Yeah, let's implement the top down first. Okay, DFS. We are currently putting the ice item with the capacity C, right? If I is smaller than 0, means that we return what? If we're running out of items, the previous item we return 0, right? Yeah. So for each item, how many choice do we have? How many choice do we have? 2. What are those?
Pick it and not pick it.
Pick it or not pick it. Okay, that's fine. So look, but obviously there's one condition is that if the capacity, yeah, is how about if the item is too heavy, then we can't pick it, right? Yeah. Okay. So like we have this answer at the beginning. This is the maximum value we can put when we considering the item. Okay. So if C is bigger or equal than the values, the weight weight of the item, current item, then we can pick it, right? Everyone, come on. We can pick it, which is answer equals max answer, okay? Actually, we don't need to put a max here because it's 0, so answer equals what? DFS I minus 1, the previous item, but we pick it, we pick it,
And we not pick it.
pick it. What happened to C if we pick it?
Plus Rocktum.
C, what happened? What happened?
Plus.
C, the
Plus
capacity.
I-
Why is it plus? Capacity.
Because you need to add it.
This C is the remaining capacity. If we pick the current weight, what happened to C?
But it's minus the thing.
Minus this weight, yeah? Weight. Okay, but if we pick it, we can obtain the value, yeah? Values I, right? Yeah? Okay, and then this will be the case of not picking it, right? Not picking it. Not picking it, what happened? What happened with the second parameter? If we don't pick it, what happened with the C? Do we need to
Just
change?
Keep it the same.
Yeah, keep it the same. And the return answer, yeah? This is the top down, okay? Top down. What's missing here? Come on. Cash. What happened if we don't put a cash?
It's explanational.
What happened if we don't put a cash?
It's
Can you-
explanational.
Why?
Because you have to keep on doing the same thing again.
Yeah.
Okay.
You can't remember it with your smooth, dumb brain.
Okay. So yeah, we put a cache to ask computer to remember the values for us. Yes. Remember, if we can look, just imagine if we call DFX like 100, 200, right? The C equals 200, and then you will call the previous value DFS I minus 1, 99, yeah, 200, and then these could be something smaller with a smaller value, right? But sometimes this value DFS IC could be used multiple times. And that's why we need to remember it once we have the value. So the next time we want this value, we just use it, yeah? Just like looking up the values in the dictionary, yeah, in the notebook. Okay? So with the bottom up, we store the values, yeah? We have this table. Look, basically, we have this table with I and then a C capacity, yeah? This is the two-dimensional table. I equals 0, first item to, yeah, etc. Till the n minus 1, yeah, we have m items, index 0 from n minus 1. The capacity 0, 1, 2, 3, etc. till C. So we are filling, we want to fill the table, right? We want to fill the table, and the top-down dynamic programming, yeah, we just ask computer to give us the bottom right value, right? And then what computer does is that, okay, you will work out the previous one, the I minus 1 values here somewhere. You probably need this value. And again, in order to calculate this value, it needs to reference the previous value, right? Here, right? Got it? This is top down. Okay, here is top, okay? This just imagination. This is top, this is bottom, okay? This is the opposite, okay? Make sense? Top down, okay, top down. Alright, bottom up, right? Bottom up. Top down because top, look, top down, this, we are given this I like 100, 200, right? We want to access this value. So look, if this is the tree, right, 100, 200 here, and then it needs to be able to calculate the value based on 99 something, yeah, a few values, yeah. Look, a few value. If you expand the tree, that's top down, right? Top down. Alright, bottom up, you calculate from the bottom up, right? So from the first row, right? Yeah. So we talk about the top bottom up. We have stored the values in the two-dimensional array, right? dp. So basically, look, this is the two-dimensional I and C. So we store this value in dp I and C, right? Yeah. Okay. So for the first number, let me just implement this. Okay. So for the first row, yeah, we store the values, and then we use the first row to compute the second row. You use the second row to compute the third row, and etc. until we get the last row, right? Well, ideally, we just want the value at here. dp n minus 1, I will be n minus 1, and then C will be capacity, right? Capacity. Can I have your attention, please,
Okay.
guys?
Guys.
Okay.
From your attention, please.
So what's the problem
Guys.
here? What's the problem here? Come on, look. let me just explain again. We calculate the first row, and then we use the first row to compute the second row. We use the second row to compute the third row. What's the problem here?
Is that we
So, first question, do I need to keep all the values in
No.
two-dimensional?
No.
Why is that?
Because
Because yeah, that's a good direction. Why we don't need to keep all the table?
because we will remember.
Look, because look here. When I calculate dpic, I just need the value of dpi minus 1, right? Nothing else. Yeah? So look, in the bottom up, right? In the bottom up, I calculate, I fill the first row, right? I fill the first row. And then I fill the second row. So how do we calculate the values, right? Filling the table,
We
bottom
need
up.
the I minus 1.
Yeah. Look, we start filling the rows, row by row. Yeah, first row, second row, third row, and then for each row we fill in the values from left to the right. So basically, it's bottom up, left to the right. Okay.
Yeah.
Okay. So now, so we only need required value for the previous row, so we can compress the space, right? Alright. So instead of declare the dpic, the two-dimensional array, we just need which dimension do we need to keep? dpi or dpc? Which dimension? Which dimension?
DP.
Which dimension? Come on. I just need the previous row, so I need to declare which dimension? dpc or dpi? Come on.
I.
Why is it dpi?
Oh, nice.
dpc, yeah? Look, because this is row, I just need this, yeah? Yeah? Okay. So I just need the dpc, right? Right? Because every time I compute the one row, I just need the previous row. So why not just keep a record of the previous row, right? And then we just can say, we can improve the time space complexity from dp, from what? From OC times n, right? That's the time and space complexity into what? The previous one, the bottom up is
C.
what? OC times n. And then
And
now,
then your time to OC.
OC.
Oh, yeah.
But the time space, the time complexity is it? The time complexity is the same, right? Because we still need to go through the procedure. Yeah, we need to iterate. There are n items. There is no way that we can make a decision. We can compute the maximum value without going through the n items. Am I right? Yeah. Okay. Okay. So let me just write a bottom up dynamic programming with the with what? With the. Let me just write a bottom up dynamic programming, okay? Define that's the knapsack 0, 1, and we have the values. Let's just call V. We have the weight and we have the C, okay? V value, W for weight and C for capacity, okay? So now look, we have to do what? We have to dp. That's we need to find out the length, the number of items, which is n. N is length of the V or length of W. It doesn't matter, okay? So now dp equals the first dimension. Okay, the first dimension is what? 0 for underscore in range. This is the second dimension, which is C plus 1, right? And then for underscore in range, which is n, right? So look, so the C, column C, and then n rows, right? Okay, and then we need to fill the first row, right? Remember, for I in range, okay, let's start from the C up to weight 0 minus 1, and I explain what's here, okay? And then dp, the first row 0. Yeah, try to understand, okay? I explain, okay? The first dimension is what? Is the item. The second dimension is the remaining, so which is the value I, okay? So what does this mean here? Remember this table, yeah? Remember this table, C, yeah?
C.
Okay, we are trying to I equals 0. We're trying to fill the first row. Okay. Initially this is all 0. Yeah? All the values 0. But we are trying to fill the rows from C up to weight 0. Weight 0. is the weight of the first item. Minus 1 is up to, remember this is up to, not including, right? So C, we change I, we iterate from C to weight I. Because why is that? The capacity is bigger than weight, then we can get a value, right? Yeah? Previously, in the previous lesson, what did we talk about? We just say, okay, from I equals, we can iterate from these rows, right? These values. But we have to check if the I is bigger than the weight. If it's smaller than the weight, what happened? If
Maybe 10.
yeah, exactly. If the weight is too heavy to put, if the first item is too heavy to put in the knapsack, we can't put it. Then the value will be 0, right? Initially it will be 0. But if the knapsack is bigger than the weight, right? Look, C up to weight, then we can put it. And what value can we get? V0, okay? V0, the first item, right? And then with this, then we can go through the value, yeah? For I in range, we can start filling the first row up to n minus row, yeah? And y 1 to n, right? And then we can go for this. It doesn't matter if you going from the left to the right or right to the left, okay? For j in range, why is that? Because look, we already have the previous row, so it doesn't matter we go from the left or right to the left, right? Because all the values we want is there, right? So doesn't matter if I calculate value from left to the right or right to the left,
No.
right? Because the previous row is already ready, right? Yeah. So range, let's say we can start from the 0 to capacity, yeah, C plus 1, and then we can do this dp ij, like this is function, yeah, equals what? Equals the max of what? We put it or we don't put it? We don't pick it, will be I minus 1 j with the same capacity, yeah? If we put it, it will be I minus 1 j minus what? The weight I, right? But when we put it, we get a value, yeah? Vi, right? But obviously, j needs to be bigger than wi. So if j bigger or equal than wi, else 0, right? Yeah? Yeah, we put this to check. Yeah? Alright, this is dynamic programming, and then return what? dp n minus 1 capacity. Okay? Yeah? Yeah? This is not new, yeah? Yeah? This is not new. We have talked about that several days ago, right? Yeah? Okay? Okay, so now we just say we want to compress, yeah, into this n times c. We want to look. This is n times c table, yeah. We just imagine we want to compress into one row, yeah. Why can we compress?
Because
Why can we compress? Why? Why can we do it? Why can we do it?
it's because
When we get the value here, we want to put the value here. So what values do we need?
the higher row.
Yeah, the previous row, just the one. Do we need the 2 rows above? No, right? We at any time we are feeding. Look, we are starting feeding from row by row. Yeah, the first the external loop is row. So we starting to feeding the rows from the bottom up. Yeah, bottom up, left to the right. Okay. Yeah, yeah. This here is top, okay? Here is bottom, okay? It's a quite, yeah. This is top. This is bottom. Do you understand?
Yeah.
Yeah. Okay. Right. The dpi only needs the dpi minus 1 and dpi minus 1, right? Okay. Okay. So now we want to be able to squeeze it. So here we don't need this. We just say dp0 times dp0 for underscore in range c plus 1, okay? Or you can say 0 times c plus 1, okay? This is the same, okay? There are 2 ways of writing it, okay? Yeah, which way you think it's easier to remember?
I think
These are the same. Which one?
the bottom one looks kind of confusing, but the top one is
Easier.
I think the top.
Okay, but some people find this one is quite easy to understand. Okay, so I have an array of 0, and I want to times this c plus 1 times. Okay, so that'll be it. Okay?
But I just
Okay, so
think the top one.
okay, yeah, that's fine. So again, here we don't need the first dimension, right? right? Because we only have one dimension, so we'll be able to get rid of the first dimension. Yeah, this will be okay. And now this will be okay. And then now here, okay, here, this is a bit tricky. So in order to compress the binary space, we have to inversely enumerate from J, from capacity up to. So we have to go from the right to the left instead of left to the right. Why is that? Because if we going from left to the right, the smaller dp0 up to J, yeah, could be overwritten. Okay, could be overwritten. Yeah. So we have to go through from the right to the left to make sure it's not overwritten. Okay, what did David just say?
Is that we should
So which way should we use?
we should use the higher level.
I know. What did you just say? You missed what did I say? I was just saying that for J in range, previously it doesn't matter. Yeah, it doesn't matter left to the right or right to the left. But now we only have one dimensional, so we need to enumerate the J from the capacity from right to the left. Okay, this is only direction that it works. Okay. Why is that? Because if you iterate from left to the right, the dp with the smaller J value will be overwritten. Okay, that's what I said. So here, I just need to go from J, from the capacity up to minus 1, okay? And then I need to go remove the first direction, yeah? dpj equals next dpj, and then I erase the first dimension. dpj minus wi plus vi, right? If j, look, okay, so look, if j bigger than wi, L is 0. So I can also get rid of this, and then I change this c up to wi minus 1, right? Right? So if I put it, then I don't need this if check, right? Make sense? Yeah? Alright?
Yeah.
So previously, look, J ranging from C up to 0, right? Up to 0. But you have to check if J is bigger or equal than Wi. If it's bigger or equal, then these dpj minus Wi makes sense, right? Plus Wi. This means that we are picking the I. Because this current remaining capacity is bigger than the weight of current item, then I can pick it, and then again, I can get the value, right? Only if J is bigger than Wi. If J is smaller than Wi, it means that this item is too big to put in the bag with J capacity, then I should get a 0, right? Yeah? You get this part. Okay, so now, look, because this J is decrementing, yeah, from C to 0. At some point, it will fall below Wj. So in this case, I can just say, that, okay, let's stop at Wi minus 1, which is up to, yeah, it will be stopping at Wi, and then I don't need this as 0, okay? The time complexity, look, On times C is the same. The space complexity, OC, right? Because we are compressing the space. Instead of using two-dimensional array, we are only using one-dimensional array which has the C plus 1 elements, right? So the space complexity is OC. So about all these three approaches, dynamic programming, which one do you think is the most efficient one in terms of time and space complexity? The last question, come on. Which one? Which one? Is it this one?
Uh-huh.
Why is that? Eric? Why is that? Which one is the most efficient? The first one, top-down, dynamic programming with the cache. Yeah, cache. It's easy to implement, right? But as I said before, the recursion with the minimization might be a bit slow compared to the bottom-up, right? The second approach, bottom-up, we create this table and we try to fill the values row by row, column by column, right? From the bottom, the first row, second row, third row, and column 1, column 0 from left to the right, okay? And the third approach, we are optimizing the space into one dimension. So the space complexity is OC, the time complexity is OC times N. So which one is the most efficient?
I think
Which one? Normally, which one, you know, this is the last series of the 0-1 nutshell, right? Because I spent 3 days, including today, to talk about this problem, and there are 3 approaches. So normally, which approach is the best? The last one, yeah. Usually I talk about the optimization, and this is the most optimal one. Well done, well done. Okay, make sense? Because the time complexity for all 3 is the same, OC times M. Although the first one, top-down dynamic programming with the cache, might be practically speaking a little bit slow compared to bottom-up. And the second approach and the third approach, the same complexity, yeah. We just change. So what did I just change? Look, I just changed it here, right? I changed this to optimize to 1 space. And then I didn't change anything here, right? I changed the second loop from left to right. I changed it to right to the left. And all this, I just remove the first dimension, right? Yeah? No much change here, right? So the second approach, the third approach is use less space, right? Use less space. And generally speaking, is the second and the third approach is equivalently performance, yeah, faster, okay, than the first one, okay. Okay, that's it for today. Yeah, thank you. Bye bye. Bye bye. Are you still here? Are you still with me?
Bye.
Bye bye. Bye bye.